Heyo there, Mr. Sutton here, bringing you the Algebra 2 3-4 lesson on using the quadratic formula. This is going to be a two-parter. So for part of this, we're going to be solving quadratic equations using the quadratic formula. It's almost like it was built for these. And for the other part, we'll see this in part 2, we're going to find and interpret the discriminant of an equation, whatever that is. So to kick this lesson off, we're going to start by tying in a concept that we just went through, completing the square. So pause the video and see if you can complete the square for ax squared plus bx plus c. So solve for x. Basically, you're going to end up with something that has a bunch of a's, b's, and c's in the final answer, and that's okay. Give it a shot. All right, so if we're completing the square for this, a couple steps we need to take first. For one thing, we want to clear out this constant of c. The a, the b, and the c are actually constants. We're going to treat them that way. X is the only true variable here. So clear out that c by subtracting it. And then we also want to divide by this a value so that we have x squared with a 1 next to it for that coefficient. So if we divide everything by a, we've got x squared plus b over ax equals negative c over a. And things are getting delightful in the early going here. Next up, we're going to complete the square on the left side. So we have to take half of this x coefficient. Half of b over a is going to be 1/2 times that, so that's going to be b over 2a. So we're going to do b over 2a squared, add that to not just the left side, but also the right side. We got to be consistent. And we can go a little bit further now from here. For the left side, I can factor this into x plus b over a quantity squared. And on the right side, I'm just going to simplify this a little bit. So we'll have a b squared over 4a squared if I square both of those. And the negative ca is still hanging around. Now before I take the square root, I want to combine the stuff on the right side. So to get a common denominator, I'm going to multiply this first fraction by 4a over 4a. That'll give me a 4a squared for both of these. So this becomes negative 4ac over 4a squared. And then to combine these into one big fraction over 4a squared, I'm going to have a negative 4ac plus b squared, but I'm going to write that as b squared minus 4ac. It looks nicer. All right, we're ready to square root both sides now. So I square root the left side. That gets rid of the square. I just have x plus b over 2a. And on the right side, I have a plus or minus, and I have the square root of b squared minus 4ac. I can't really do anything else with that square root up there. Downstairs, though, the square root of 4a squared is going to be 2a. And one other little step here. To get x truly alone, I'm going to subtract b over 2a to the other side. So if I do that, I get a fraction. On the numerator, since these both have the same denominator, on the numerator I have a negative b from subtracting negative b over 2a. I still have the plus or minus and the square root of b squared minus 4ac. And then in the denominator, we have our common denominator of 2a. Now, this thing that I just wrote by completing the square on the quadratic equation in standard form, this is called the quadratic formula. And it turns out this is a formula that will allow you to solve any quadratic that is in the form ax squared plus bx plus c. So pretty powerful. Let's go ahead and use this thing. So here we are with our first big example. They're telling us to solve this using the quadratic formula. Now this is the sort of equation that normally we would use completing the square on, but we've got this quadratic formula that essentially does everything completing the square does, just in one formula instead of a bunch of steps. So in order to use the formula, it's fairly straightforward. There's really only two things you need to do. Step one is, if it's not already, put your equation in standard form. That's ax squared plus bx plus c equals 0. So basically zero this thing out. And then write out a, b, and c. So right now we see this thing is not zeroed out. So to get it that way, we're going to subtract 8x from both sides. And to put it in really standard form, I want to make sure that 8x goes between the 11x squared and the 1, like so. Now we're going to write out a, b, and c. Now, could we have figured out a, b, and c without rearranging things? Probably, but it's much easier if it's just in order with the correct sign. So we've got an a value of 11, B value is going to be negative 8, and then our C value is going to be 1. And this one, it was kind of straightforward what A, B, and C are, but if you were, sometimes it's a little trickier. If you were missing, for example, this x term in the middle, then you would have a B value of 0. If you were missing a constant, then you would have a C value of 0. So you just got to kind of be on the lookout for those weird cases. All right, so you've got A, B, and C written out. Now what? Well, I would recommend you write out the quadratic formula. Negative b plus or minus square root of b squared minus 4ac all over 2a, all of that. It's a good idea to write it the first few times you use it to help you remember it. And then just basically plug in a, b, and c and simplify as much as you can. So if you're up for the challenge, feel free to pause the video, plug all that in, and see if you can simplify it into simplest radical form. All right, so let's see how that went. So there's 5 different places that we're plugging things in. So I'm just having a bunch of kind of skeleton parentheses here ready for some input. So we've got negative b, that's negative 8. And then inside here, b gets used again, so this is negative b squared. Minus 4 times, well now we've got a being used, that's 11, times c, so that's 1. And I color-coded this just to help us here. And then a, we're using that again, so that's 11 down there. All right, let's go through and simplify a little bit more. So we have negative 8, that's positive 8. And negative 8 squared, that's going to be positive 64. And notice I used parentheses here so I don't lose that negative sign that's being multiplied by itself. And then we have 4 times 11 times 1, that's 44 that we're subtracting there. All over 2 times 11 is 22. We can go a little bit further and call this stuff inside here 20. And are we fully simplified? Well, it looks like this radical can definitely be broken down a little bit more. 20 is divisible by the perfect square 4. And we might also be able to reduce the fraction. So the process to follow is you want to simplify the radical first and then reduce the fraction. Right now, we can't really touch this 20, even though 8, 22, and 20 would be divisible by the same number. The only thing that we can touch with this 8 and this 20 is anything that comes outside the radical. Because the inside stuff, this isn't really 20. This is the square root of 20. It's some crazy decimal. So what can I split 20 up into? Well, I can make that 4 times 5. And then I can square root the 4 to get a 2. So this is 8 plus or minus 2 radical 5 over 22. Once I've got this radical simplified, now I'm going to look at my numbers to see if I can reduce this fraction. And the rule is you can only reduce if you can reduce all 3 of these numbers here. So the 8, the 2, and the 22. Those are all reducible by 2. So I can reduce the 8 to a 4. This 2 becomes a 1 that I'm not going to have to write in a minute. And then the 22 is an 11. So when the dust clears, we've got 4 plus or minus 1 radical 5, so just plus or minus radical 5, all over 11. Here's another example for us to try out using the quadratic formula. So pause the video and give it a shot. All right, so first, just as before, we want to put this in standard form, because if we don't, then we're going to be picking maybe the wrong numbers for A, B, and C. So you got some options here. One option is you could subtract the 13 over to the left side. That would be the fastest way to get standard form. However, I'm going to actually move everything over to the right side. And the reason I'm doing that is because I like to have a positive a value as often as I can. It's just annoying if that the a value is negative in 2 different spots. So I'm going to move the x squared over to the right side of the equation. That makes it positive. I'm going to subtract the 4x over to the right side. And that 13 is already over there, so that's still a plus 13. And all of that now equals 0. Now, it's also worth doing a quick double check on a problem like this, where you have an a value here of 1. I mean, this looks like, you know, we could at least quickly check to see if it's factorable. So are there 2 things that multiply to 13 and add up to negative 4? Well, definitely not. 1 and 13 is the only show in town, so that's not going to work. So we go to quadratic formula. All right, so our a value then, the way we have it set up here is negative 1. B value, negative 4. C value, 13. Now, if you moved the 13 over to the left and you had an a value of negative 1, then your b would have been a positive 4, and your c would have been a negative 13. So you can get the same answer if all three of these plug-in values switch signs. They have to all of them switch signs at the same time. But let's use what we've got here. So here's our quadratic formula again. And there's all sorts of ways you can remember this. There's even like a funny song, I think, that you can play to remember this. In any case, plug in stuff in. We have negative 4 plus or minus square root of negative 4 squared, and again, use that parentheses, minus 4 times 1 times 13, all over 2 times 1. So negative 4 is 4, 2 times 1 is 2, so I can usually do those in rapid succession. Now there's this inside stuff, which, by the way, all this stuff inside the square root, it has a special name we're going to learn about in the next part of the lesson. Just to plant the seeds, this is called the discriminant, and this really determines what type of answers you get, but we'll get there later. So we have 16 minus, let's see here, 4 times 1 is 4, times 13 is 52. 16 minus 52, that's negative 36. And to simplify this, first we're going to simplify the radical. We can take out an I and then square root the 36 to get plus or minus 6i. And then dividing each of these by 2 or reducing by 2, we have 2 plus or minus 3i. And we're not going to write over 1 because that's just silly. So yeah, this one shows that quadratic formula can get us even imaginary answers. So this was all our first look at quadratic formula. This is the end of part 1. Feel free to pause the video, do a problem set or so, and then come back for some more learning afterwards. Welcome back. Thanks for joining us for part 2 of this quadratic formula lesson. In this one, we'll be later on looking at the discriminant, whatever that is. And right now, we're actually going to start with an application of quadratic formula, which is to say an application of quadratic equations, because all the formula does is solve your equation. All right, so as I'm recording this, this is actually pretty close to Patriots Day, where we celebrate the battles of Lexington, Concord, and Menotomy. So there's reenactments going on of those battles. So let's talk about a reenactment for this problem. It seems fitting with the times here. Let's say we have some soldiers from this reenactment on a hill launching some Nerf arrows, and we've got some rebels down below yelling, "Freedom!" So we've got these Nerf arrows. We're going to fire those up and down, and again, you know, they're going to pretend to be scared, but these will, if they actually do hit anybody, they'll just bounce harmlessly off. So let's talk about the physics involved here. An arrow's height, h, in feet at time t seconds is given by this h of t formula. This is a good one to write down. Negative 16t squared plus v0t plus s0, where v0 is called this is the initial speed of the arrow, the velocity, and this s0 here is the initial launch height. So the way this formula is set up, this negative 16t squared is basically the effects of gravity, and that's being kind of countered by your velocity that you shoot this thing up in, and you also have to factor in the height that the arrow started at. With this framework in mind, we want to know how long will these Nerf arrows, if they're fired at 56 feet per second, take to reach the other reenactment players 120 feet below the launch point. So these are fired up in the air and they come back down in a nice little parabola. So if we're using this formula here, first off, pause the video and see if you can figure out where to plug things in. Alright, so let's see what we came up with here. If we're using this formula, we're basically asking at what t value, we're solving for t, do we achieve an h value of, well, it's 120 feet below, so we want this value to be negative 120. And what else is changing in this formula? Well, this negative 16t squared is going to stay the same. T is what we're solving for. v0 in this case, this is the initial velocity, 56 feet per second, so we'll put that in there. And then how about our initial height? Well, if these folks are 120 feet below, we can basically assume that this height, we'll just call this 0. I mean, there might be like a couple feet if we talk about, the arrow was fired from 3 feet above the ground, but we're not going to worry about that for this little problem here. So now the question is, how do we solve this thing? Well, we've got lots of ways we could try to solve it, but I suggest we do the quadratic formula, because that's what this lesson is all about. So here is the equation that we're trying to solve for our real-life reenactment problem, if that's a thing. So I'm going to get this in standard form to start with. We'll do the first few steps of this together, because there's something I want to show you here. So just like before, I'm going to try to make this negative a positive by moving it over to the other side. So I'm going to add 16t squared over to the left side, and I'll then subtract 56t to get it to be with the t squared. And then finally, this negative 120 is still there, and we have 0 on the other side. Great. So at this point, we could go ahead and plug these numbers into the quadratic formula, and that would be fine. We would eventually get the answer. However, one trick you can do is if you see that you can divide everything by a constant, you are actually allowed to divide by a constant greatest common factor, or even if it isn't the greatest common factor, you can divide by whatever you want before using the quadratic formula. And it may be helpful to do that because you could get smaller numbers to plug in and might not have to use a calculator to crunch the numbers. So out of all these terms here, I think 8 is the biggest number that will still let us have whole numbers after we divide by it. So if I divide by 8, that'll give me 2t squared minus 7t minus, I think that's going to be 15, equals 0. Again, we could have gone straight to quadratic formula in the beginning here, but this one gives us some nicer numbers to work with. So with that said, pause the video and see if you can figure out how long those arrows, those Nerf arrows, take to come back down. All right, so we've got an a value of 2, b value of negative 7, c value of negative 15. So using our quadratic formula, and notice this time I wrote t equals instead of x equals, just to be consistent with our variables here. This is going to be negative 7 plus or minus square root of negative 7 squared minus 4 times 2 times negative 15 all over 2 times the a value 2. So that's positive 7 plus or minus the square root of 49. And let me see, we've got 2 negatives, so this whole thing is going to be a positive here. We have, I'm going to do these in a different order than they're listed, so it's easier for me to do in my head. 2 times 15 is 30, 4 times 30 is 120, so this is a plus 120. All of that over 4. So this stuff inside here simplifies to 169, which I happen to know is a perfect square, the square root of that being 13. All right, so this is good as far as it goes, but it's not fully simplified because we're able to combine the terms to the left and the right of this plus and minus, so we are obligated to do that. And also, if somebody's asking for the answer to a real-life problem, this is probably not a very helpful answer to most people. So we have 7 minus 13 over 4. That's one of our 2 branches. That's negative 6 over 4, which I can reduce to negative 3 halves. And then we have 7 plus 13 over 4. That's 20 over 4, which I can reduce to 5. So in terms of our real-life answer, these are both times that the arrows take to make it down to that other group of reenactment soldiers. So which of these seems the most realistic? Well, 5 seconds makes sense. 5 seconds after the arrows are fired, they come back down. Negative 3 halves, negative 1.5 seconds, doesn't really make a whole lot of sense. This whole negative time thing doesn't really work for most problems. So if this were a real-life problem, we would just take the 5 and discard this other one. So we've done a few problems where we've gotten some practice using the quadratic formula, both on regular math problems and on kind of application problems. We're going to zero in on one piece of the quadratic formula now called the discriminant, which gives us some potentially helpful information. So the discriminant, just to officially define it here, is the b squared minus 4ac part of the quadratic formula. It's all that stuff that's under that square root that you're plussing and minusing. So because you're square rooting all this stuff, and because different things happen when you square root different types of numbers, we can use the discriminant to determine the number and the types of solutions. So I've got a little table here that we will use. Based on the value of the discriminant, this will tell us what types of solutions we have. So let's say that we do our discriminant here and we get a positive number. So we're doing plus or minus the square root of some positive number. Well, when you take the square root of a positive number, you get a number that's not 0, and then you're going to be adding and subtracting that number. So that's going to give you, and it's a real number, so that's going to give you 2 real solutions. One for when you subtract whatever this came out to, one for when you add it. We could even break that down further if we wanted to, like if b squared minus 4ac is a perfect square, something that when you square root it you just get a rational number, then that would even tell you that you had 2 rational solutions. But we're not doing that level of analysis here. Let's look at another situation though. Let's say that you do b squared minus 4ac and it comes out to exactly 0. If you're taking the square root of 0, that's just 0. If I add and subtract 0, I'm not really getting 2 different results from doing that. I'm just getting one result that looks a little different. So this ends up giving us just one real solution, and I'll take the s off of that. There we go, one real solution if our discriminant's 0. Now, the other case we haven't looked at is if our discriminant comes out negative. If you're square rooting a negative, then you're not getting any real solutions, but you're going to be getting 2 imaginary solutions. You're getting a real number plus or minus whatever your imaginary component was. So now that we've got this background, we're going to do a few examples to see how this works in practice. So here's what these problems look like. We're given a quadratic equation. It may or may not be in standard form, and they're telling us to find the discriminant and describe the number and types of solutions. This process is pretty straightforward. You've got the discriminant, b squared minus 4ac. That's our formula that we'll use every time, and I'll just call this big D for discriminant. And basically just have to plug in a, b, and c and compare it to 0. Is it bigger? Is it 0? Is it less than 0? And that tells you based on that table what our solutions look like. So pause the video and give this a test drive. Alright, so plugging things in. We have a b value of -6, so we have -6 squared minus 4 times the a value, we have an invisible 1 here, times the c value 10. So this is 36 minus 40, which is going to come out to -4. Now the important piece here is -4 is less than 0. So that tells us, because our discriminant is negative, that we have 2 imaginary solutions. Now, why might this be helpful to know? Well, if you have an equation and you want to see if it has any real solutions before you bother figuring out what those are, this is a little bit faster than doing the whole quadratic formula out. All right, so we'll do another example here. We've got x squared minus 6x plus 9 equals 0. Pause the video and give this one a shot. All right, so I've got my discriminant formula. I'll just write that every time. We have b squared, again, that's going to be -6, minus we have 4 times the a value that is, again, a positive 1, and now the c value is 9. So we only changed one little thing. Will it make a difference? Well, we still have 36. Now we have -36, so that comes out to exactly 0. Because the discriminant is 0, that tells us that we have one real solution. All right, we'll do one more. Here you go. X squared minus 6x plus 8. So again, not a lot changing. We're just changing this c value and by 1, right, and seeing what happens. Pause the video, check it out. All right, so we have our discriminant. We have -6 squared again, minus 4 times 1 times positive 8. Now I've got 36 minus 32. Which comes out to positive 4. Since that is a positive number, this tells us we have 2 real solutions. And if we wanted to go a little bit further, since 4 is a perfect square, that means that we would actually have 2 rational solutions as well, if we needed to know that. That might be useful information because rational solutions mean that this equation was factorable. To wrap this lesson up, I'm going to end on kind of a cute note here. So, or a cube note, as it were. So you might be wondering, well, there's this quadratic formula that solves any quadratic equation. That's pretty cool. Is there something analogous for solving all cubic equations? If I have something in the form ax cubed plus bx squared plus cx plus d equals 0, is there kind of a magic formula for that? And it turns out there is. And here it is. If you were curious, I would not recommend you write this down. It's a lot. It actually has 3 different components. So I'm going to call the first one x1. And here's all the stuff you would have to do for x1. So we have an a, b, c, and d that we're plugging in. We're doing fractions. We're doing some square roots inside of square roots. We're cubing things. It's pretty wild. And then there's this random minus b over 3a thing at the end. This is a real thing. I've actually programmed this into a graphing calculator and used it to make sure it works, and it does. X2, the second solution, is all of this stuff. If you thought the first solution was pretty gnarly, well, this is pretty wild. And then there's X3, which looks a lot like X2, but there's a few minor differences in terms of signs and things. So yeah, there's a cubic formula, but it's a little bit more than the quadratic formula. I think there's a quartic formula too, and it's even crazier than this. Now here's one thing I did want to kind of point out that's kind of neat. You'll notice that there's another letter in addition to A, B, C, and D, and of course X. It's kind of hard to see though. It's at the very end. Here's that other letter. It's an I, and it's another I down here. If you were wondering why somebody came up with the crazy idea of imaginary numbers, this was actually the reason. They were trying to find a way to make this cubic formula actually work, and they found they needed imaginary numbers to do it. Kind of crazy. So anyway, with that craziness established here, till next time, this is Mr. Sutton signing off.